The art of speech, at least for GPT, is a probabilistic game. Now, previously we've discussed the transformer architecture and the extensive process it goes through in order to generate a context length number of probability distributions across the token vocabulary. Go watch the previous episode if you don't know what I'm talking about and to understand what that is. And after that, a selection method is used to select an individual token out of the probability distribution, which is then displayed to the user, which is you. Now, essentially, in the last episode, we've broken down the linear and softmax operation that goes down after the transformer architecture, which generates a probability distribution. So essentially, you got your context window, right? And there is a probability distribution for each point in that context window. So essentially, you can imagine your context window to be like 1048, right? 1048. Well, there would be 1048 probability distributions. And what is this probability distribution? Well, it's also another array of little probabilities, little values, in which, like, so imagine you have like a probability distribution. The first value you have there is like 0.01 or something like that, right? It's a probability, the probability of that token being chosen, and the position of that token, which is like the very first position, that's the actual token. Like, it's the first token in the token .json vocabulary that we've looked at in episode 2. That's what it is. And so these probability distributions, there's 1048 of them for each position. Like, if you can look at this beautiful illustration that I put here, for each position there's an entire, like, imagine if you got like 80k different words or like 20k different words in your token vocabulary. Well, there's going to be 20k different probabilities, each like probability, the position of which is like the actual token. Like, this may be like the 9,000th position. Well, that's the 9,000th token, and the probability of the 9,000th token being chosen is this, right, for example. So, but we don't actually need 1048 probability distributions. I mean, the model does that because it just has to do it over the entire context length. It can't just like dynamically adjust for each position, but we need it for a specific one. So let's just look at this example here. How do you think, where would the valid probability distribution be? Because softmax and linear and softmax have now generated a probability distribution for the first position, for the second position, which is like, which token should I put on the second position? That's illogical because we already have, like, essentially there's the user sequence, and then there's like an empty space of the GPT, and the very last token, that's like the 4,000th token if you have like a context length of 4,000. And it's illogical to think, what can I generate over here, because it's already, like, the user already provided the sequence. So you just have to look at what's the next token, right? So yes, if you guessed correctly, it's position 15, and the probability distribution at position 15 would be the actual one we would care about. It actually can't see positions, like the transformer architecture literally could not see positions from the 14th one. Like, only these were available to it, and these ones were not because of something called a causal mask. We'll break that down in coming episodes, but anyway, it enforces auto regression and all this stuff, but we'll break that down later. So it can't even see these positions, so like literally it cannot say what's the position, what's for position 17, right? Because it hasn't even seen position 16 and position 15. Now, the reason why I can go for position 15 is because it's looked at all of the other positions up until that point, and so it can accurately say, based on all of these, based on the user input and the user input only, and not some kind of like empty token at position 17, not that, what's the next token that should be chosen, and which is why position 15 is the valid probability distribution. Okay, so now that we've cut through that, I'll give you a little bit of analogy for understanding. Just don't keep reading, okay? You just have a very short attention span. Just look here, okay? Actually, don't look there. Look at my face instead of looking there. You probably have a short attention span, so don't do that. Anyway, I'm going to give you a little bit of analogy to actually picture this probability distribution. So this is your pie chart, right? And there's obviously context window times of that pie chart. So for example, 4,000 such pie charts. Essentially, there's a pie. Let's say we have a context length of 10, just for convenience. So that could actually 8. So that could be easier for me to explain. And I can just make the pie slices like this immediately. Actually, let me just do something like 9. Right. So you got this beautiful pie. Now the reason why I drew it so uneven is for you to understand how it actually works. So you can imagine in this analogy that the location of the pie, like it's at the 0th degree or whatever, is the token itself. So essentially the pie slice right here is the token itself, and the size of the pie is the likelihood of the token being chosen. So this like the pie slice over here is quite big, so the probability of it is pretty high, so it would be 0.4. And by the way, linear and softmax ensures that the probability distribution adds up to 1, right? I think I've said that in the previous episode. It adds up to 1, so it's all like a percentage, so this would be 40%, right? It's obviously not in terms of size, but you get the point, right? I could maybe illustrate it like that, and this would be 20%, right? So the pie itself is the token, and the size of the pie is the likelihood of the token being chosen. Now, in a different way, I can give you the lottery analogy. So essentially, the size of the pie slice over here is the amount of lottery tickets bought by one person, and the pie slice itself is the person who bought those lottery tickets. And so you can imagine the lottery tickets, the amount of lottery tickets is the greatness of the probability, like the number of the probability. So it's whether it's 0.2 or 0.19 or whatever. And the actual token itself is the person, right, in this analogy. So if you don't understand how we can like identify the actual token, well, just look at this. If we have a probability distribution of like, let's say our context is length 9, we have this. Essentially, everything here adds up to 1. I'm not gonna break down how like I'm not gonna try to make it all sum up to 1, but just essentially just imagine like as if it adds up to 1, and you got all these little values, right, up until the very end to the 9th token, to the 9th position, which is like 0.01 or something like that, right? The position of the token is the actual token, or the position of the probability is the actual token itself. So this is at the 1st position, this is at the 2nd position, 3rd position, this is the 9th position, right? Well, these positions are not just positions, the positions are actually what we like look at as tokens, right? So at the 1st position, like the 1st token, the likelihood of it being chosen is 10%, right? The likelihood of the 2nd token being chosen, and by the way, the like token 2, for example, in the vocabulary could be a special token, and this is like 12%, right? And then a 9th token, which is like, it could be like a special symbol or a letter or something like that. It has the probability, like the chance of being chosen as 1% or whatever like that. And the positions are the tokens, the probabilities are the chance of it being chosen, okay? So you have to understand that before we actually deep dive into the token selection methods. So let's go down the line. We have 5 main token generation methods known today for NLP and GPTs. We have greedy decoding, right? We have greedy decoding over here. Then we have beam search. So these are all the token generation methods we have today for NLP. Okay, NLP and specifically GPT. Okay, so let's break this down. Now, greedy decoding. How does it actually work? So you have this probability distribution, and what it does is literally just grabs the biggest one out of it. So you got 0.4, 0.6. Like let's say the context window size is 2. And in the probability distribution, there's only 2, or not the context window size, the amount of tokens in the vocabulary. There will be about 20,000 or something, but let's just, for simplicity, say it's 2 because I can't draw 20,000. It will just take the largest probability and that's it. Okay, first, 2nd token selected, right? Of these 2 positions, 2nd token selected, boom, that's our new token. Or maybe it's like zero-based indexing, so it would be like that, but it's semantics, right? So that's the token chosen. And let me just keep this drawing over here. Let me just do that. Vocab equals 2. So like it just grabs that one, grab biggest one. Let me just that. Grab biggest one, and then 2. You just get your token 2. It's very simple. So essentially the result of this by just grabbing out the highest probability token is that it is very deterministic. So it just gets it out, gets the highest probability token, and it usually can make the text quite quality, especially if your context window length is kind of like shorter. But the problem comes when it becomes very highly predictable, because you're just selecting the highest probability, which is essentially in the training process, you have your tokens, and the highest probability value, strictly the highest probability value, will probably just be what fit for the data set, to satisfy what input sequence was given into the data set. And there's not much creativity that goes into it, not much thought that goes into it. It just spits out the highest probability. And sometimes the text can degenerate, right? Not in that sense, but in the sense that it becomes nonsensical. So it just spews out whatever. It starts it says, imagine that this is logical text and this is nonsensical. Actually, no, never mind. Imagine that this is logical text and this is nonsensical text. So it begins with if you tell it, hey, tell me about how GPTs work, it says, well, GPTs work like this, and then it just starts spewing out random stuff, or maybe it just starts repeating the same stuff over and over again because it's just the highest probability token. Let's just grab that, and that's the problem. So yeah, it becomes nonsensical. So limitations, so benefits, let me just write here, benefits, is that it can be quality sometimes, quality initially, there we go, let's say quality initially, but then degrades over time. Degrades, predictable. So that was quick, but now we move on to beam search, which is a different form. It's kind of an advanced form of greedy decoding, which attempts to mitigate the quality issue, or the degrading issue of the greedy decoding token selection method. So essentially, you first define a number of beams. This is an essential number that you have to define. Let's just say it's NB, number of beams, and it has to be greater than 1, but less than the vocabulary size. So if you have 30,000 vocabulary tokens, it has to be less than that, right? And the reason why it has to be less than 1, because if it is 1, it's just greedy decoding at that point. If it isn't, then there's multiple beams, and it cannot be vocabulary size like all of them. Actually, no, it can be. So it can just go like that. Essentially, over 1, okay? And it cannot exceed V, because it's going to be essentially, as you can see in this image, selecting certain tokens out of the token vocabulary, and then it's going to keep branching off into that. And if NB equals to V, then it's just going to select all and then just keep branching off and selecting all. But that's very, very difficult to do, especially with large context windows, so that's never done. NB may be 5 at best, but whatever. So essentially, how does this work? You define a number NB. In this case, NB is equal to 2, okay? And then what this does is essentially select the 2 highest probability tokens. So let's say you got the V is 5, right? 1, 2, 3, 4, 5. V is 5, and you got this user input, right? Hold on, user input, and then you're supposed to generate the next token. So you're doing this process over here, which is you have the vocabulary of 5. You select this token and that token at the same time. You don't display it yet. No display. Okay, no display yet. You select 2 tokens that are of highest probability. You could imagine if you got 0.6 and then 0.1 and then 0.4 and then 0. I mean, this all has to add up to 1, but we're just gonna go with what we have here. And you have this. Right? So what is going to be selected? The 2 highest probability tokens, this one and that one, which is A and C. So we go and select A and C. Let me just erase all of this quickly. So we go and select A and C, and now we have two sequences that the model is processing at once. Now you can probably see the problem with this already, how computationally intensive that would be. But anyway, then at this point, the number of beams is just forgotten about. It's just select 1 token here and then select 1 token over here. And then it just keeps generating like that over the probability distribution after doing this branch off. And then it has generated two of these. So essentially you can see beam search collects the highest probability tokens, and then the second token, yeah, and so on. After the token generation is completed through an end, like completed by an end of sequence or end of reply token, which usually does not happen in parallel as displayed above. So like, for example, here it's displayed as though they end both at the same time. This one could end earlier than this one, like keep on generating. This one could stop generation earlier than the other one, right? But anyway, after the token generation is completed, the sequence with the highest total probability mass, or the highest cumulative probability, is chosen as the final output. So essentially you got ABD. Imagine like you got A, which was like, what did we do? 0.6. So we got A, we got B, say B was like 0.1 or 0, and then D was 0.6 or 0.2, something like that, right? And the total of this, the cumulative probability, would be 0.1 plus 0, or 0.6 plus 0.1. All this stuff would together be 0.9. I don't know why I struggled there with that math, but anyway, that's the total. And with CED, it may be like, what did we have? 0.4, 0.3, 0.1, something like that, right? This in total would be 0.8. So you have these cumulative probability, not masses, but values, and the one with the higher value is the one that's actually chosen to display to the user. So actually this would be chosen right here, because in this hypothetical scenario it had more, so ABD will be displayed. So you got the user over here, boom boom, GPT, it just goes ABD, right, like that. Now what are the benefits, or what are the results of this type of computation? Well, it's typically high quality and coherent text, because you're actually going, and like the more beams you have, the more quality it will become, because it's just branching off and then doing that generation like that afterwards. And it's less probable to produce nonsensical or repetitive text. It still can, because it's greedy decoding, but less probable anyway. But it's too resource intensive and too slow at generation, since the model has to process multiple different sequences simultaneously. The amount of sequences processed simultaneously equals to batch size times number of beams, and that's a lot. So if you got a batch size, well, for instance, okay, ChatGPT 3 had a batch size of 3.2 million, then times the beams, which is like 3 or 5 or whatever you want to set it at. Let's say it's 2. 6.2 million sequences processed in parallel. That's a lot, very computationally intensive, and the model will probably not be able to generate like it properly. So it's not worth it, at least in my opinion. But and yeah, this is beam search is kind of archaic nowadays. Now hold on a second. You're very clearly interested in GPTs, right? You want to code up one on your own. Let's be real. You want to implement one in Python, so you're trying to figure out how it works. And I'm here to help. Right. I'm also very interested in this field. You and I are very interested in this field, and we want to innovate in this space. And so it's very hard to research all this stuff when it's all like kind of like private information, or it's like not really spelled out properly. Maybe there's some concepts that are very vague still. I'm here to help even further than these free YouTube courses that you're looking at right now. So I suggest right now you go and click on the link in the description and buy my course called The Innovator's Guide. This course spells out exactly how to build GPTs in code in Python, like in TensorFlow. You're fully going to code up and train a model on a data set and everything like that. You're going to have an actual model to use and to just use for whatever purpose. And the reason why I think this course is great is because you could either be shooting in the dark for an entire year trying to research about GPTs and all this like weird information that's kind of not really, like it's very vague, you don't really understand most of it, a lot of vague concepts. Or you could go with this course right now and like build your own GPT in a month from now. How does that sound, right? So go and click on the link in the description right now. It's at early access. The price will rise in the near future. So go and click that right now. But we move on to temperature sampling, which is a little bit more modern, but it still has been topped by something else, but we'll break that down later. Now, remember when we talked about linear and softmax, right? Linear to softmax. Well, here we actually substitute softmax with temperature scaling. It's a little bit odd to realize, but this is how it would look like. Temp scaling formula, which is displayed over here, right? Maybe I can draw it for you beautifully. We'll break this formula down. It's not that complicated, but yeah, you got P xi equals e to the power of xi over t over summation vj1 ejx x. Yeah, there we go. As much as I could fit it in, I tried. So it's replaced with that. So softmax, the actual softmax function is like this, exi over this, right? Over vj1 exj, right? There's no division by t, but this is like the altered softmax essentially. And then from that one, we select it randomly, but you'll see right now, okay? So let's break this down step by step. Oh my god, why am I erasing that one? So yeah, there we go. You have this over here. How does it work? So pxi is the individual an individual probability. So softmax generates probabilities. Well, in this case, this generates probabilities, and this is the what is it? An individual value of the linear layer operation, otherwise known as a logit. So the x is the logits, right? X logits, which are just raw model predictions, raw model calculations, not processed yet, and I is a certain point in those logits. So that's if I is 1, then it's going to be like the first position in the logits in total, and P just creates an entire thing, right? So and P and when I said entire thing means entire probability distribution. So before we said we already have a probability distribution, but here we're creating it right now. So we have this, right? And essentially, if I would like to put it in words, which is way easier to do, for every element in the logits, for every logit in the logits, divide, and okay, this is very difficult to say, first divide it by t, and then have it be an exponent of the Euler's number, which we'll break down right now, and divide it by the sum of the same thing that's summed up like all together, and that's also an exponent of the Euler's number divided by t. So this is just summation, by the way. I just wanted you to remember this is summation. First, we have to break down Euler's number. Maybe you've heard of it, maybe you haven't, but essentially what Euler's number is a fantastic way to work with exponentials and to work with places where there's natural growth. So here you see Euler's numbers is a mathematical constant, which is special because it's derivative. I mean, if you don't know what derivatives are, it's just like rate of change. So it's like you've probably gone through the whole rise over run thing, right? This is kind of rise over run, except for like functions which are not fully like linear like this, right? Rate of change essentially, right? Derivatives are rate of change, and ex, right? This little thing, e is the number e is actually like, you know, like pi, right? You know, pi is like 3.14. Well, this is the same thing. It's 2.718, I believe, and then it just keeps going forever. And we found out that 2.718 to the power of x, the derivative of this, the rate of change of this, the amount of changes there is for each y value, for each tiny step in the y value, per each tiny step in the x value, in like, if you could imagine like a graph over here, each tiny step in the y value for each tiny step in the x value, we've found out that the rate of change for this is actually 2.718 to the power of x, right? The derivative is equal to the function itself. And why is this a pretty cool feature? Is because it allows us to, let me just draw it here, more small over here. It actually allows us to work with something called natural growth. So essentially, natural growth is where it follows a certain rule in which the growth is proportional to its past value. Like, for example, interest rates. So we'll just go off topic a little bit here from GPTs, but we have like 100. Imagine you put into your bank account $100 and you get 10% interest over 5 years. right? Now, the typical formula that you would generate to see how much interest you would get at the 5th year or whatever would be A equals P1 times 1 plus R to the power of T. But we have found out that, let's just look at this first. So this essentially tells you, okay, in a year you're going to get $110. In the next year you're going to get $121. We found out that the Euler's number can work with natural growth cases in which like it's proportional to its last value. So how did you find out that the next year you're going to get 121 is by looking at this, getting 10% from that and adding it onto that, which gave you 121, which is like this natural growth pattern. And we found out that Euler's number is actually correct in giving us that. So if we have this thing, instead of using this, A would actually become E, so P1 is actually like $100, right? So you use 100, this formula would be 100 times 1 plus 0.1 to the power of T, and T is like the next, like the year, right? This would be T equals 1, and then this would be T equals 2, right? Well, you could actually swap this formula for P1, which is $100, let me just make it more simple for you, times E to the power of 0.1 T, and T is like multiplication, right? It's literally the same thing, essentially. It almost gives us the exact same results. And if you do, right, just go ahead on your calculator right now and do this, and make T equal to 1, which is like the first year, it would literally give you 110, almost approximately. There would be a slight decimal floating point value after that, but that's fine. And then you do T equals 2, it will give you this, I mean almost, right? It will give you 1 to 2.1, which is very close to it, and it just gives you, you could essentially substitute the formula and it would be approximately right. Which is what makes the Euler's number pretty cool in that regard. It allows you to work with natural growth situations. And now how does this actually relate to our logits, this Euler number? Well, simply put, the fact that it has natural growth, and the fact that it is like the derivative of d, like, I mean, I don't know, how do you represent this d like that, right? The derivative is literally equal to itself. The fact that this is the case, it helps with back propagation. Essentially, what back propagation is, it is a process where you go back and kind of calculate derivatives in order to make a change in the model. I've broken this down in last episode about how back propagation is done in order to, it's going to be covered more extensively in coming episodes, but it's done so that like we collect derivatives and then we can adjust the model's weights and biases so that we can like make more accurate judgments. And it's way easier to collect derivatives when the derivative of the number of the function is literally equal to itself, right? Which is something that we have to remember. But there's also something else that occurs here, which is important to cover. It's the difference between the logits. We will break this down with the variable t, the parameter, essentially, which leads to, like, here I wrote that this exponentiation creates greater values to become even greater than 1 values to become even greater, and then less than 1 values to become even smaller. We'll break that down over here already with the pie charts. But anyway, so we have the variable t, which is a parameter. So you got e to the power xi divided by t. The t is done here to cause even more of a diminishment or a flattening effect. So here we'll look at this later, but essentially, if you got t, which by the way, t is set between t equals, t is in range of, like, how do you do that? T is a member of, I don't know, like, no, how is it? T is a member of this little area, 0.0 to 2.0. Right, anywhere from 0.0 to 2.0, it is set. So if you have t equals 0.6, essentially what it does, if you have this e to the power of xi, what if xi is equal to like what, 1, right? 0.6, then previously you would have just done e to the power of 1, which would have been 2.718, but now that you have 0.6 in the picture, it makes this even bigger, which is like, well, 1. I don't know how much it is, but I'm just going to say 1.4, which is going to make the Euler's number even bigger than what it would have been, which amplifies the value, okay? But what if the value, the xi, is smaller than the temperature? Then, like, you got 0.4, 0.6, right? I also don't know how much this is, man. 1.5, I'm an idiot, bro. 0.666, I think, yeah. So it makes the Euler's number even smaller, which is like, this is almost a square root, right? So it makes it even smaller. So this is like a sharpening effect. You'll see a bit later, but this causes a sharpening effect where smaller values get even smaller, higher values get even bigger. And it depends on the temperature. If you have 0.9, right, for example, that will actually cause more like diminishment, even with greater values, even with values that were kind of large, they will still get diminished as well. Because like if you have like 1,000, right, and you divide it by 0.9, because if you had 0.8, which would otherwise escape diminishment if it was like, if t was 0.6, but now it's 0.9, so it's going to get diminished because e to the power of this, it would actually be smaller, so boom, yeah. Actually, no, it wouldn't be smaller in this context, like the number wouldn't become smaller, but relative to the resultant probability distribution, it would be smaller. Now, if you're not understanding these technical terms, I'm very sorry, but you'll have to really like think and visualize it through, because I can't really dumb them down much, because otherwise the explanation becomes very dull. Anyway, you got this. Okay, if, however, t is over 1, and by the way, don't set t to 1, else it's literally useless. It's just dividing it by 1. But t, if it's like 1.5, right, then it flattens the distribution. So if you got 1,000, right, and you divide it by 1.5, if you had 0.9, it would actually amplify the number, right? And then Euler's number would get amplified. But if you have 1,000 and you divide by 1.5, the value is going to be smaller, right? It's going to be what? I don't know, man. My math has been slacking. 15 or 150? I'm not sure. But anyway, you get that, and you do that. It's a smaller value now, and the Euler's number is going to be smaller and all that stuff. Sometimes it's actually not smaller because of like as I told you before, 0.8 to 0.9, all this stuff. Like relative to the probability distribution, it will actually be smaller. Actually, no, sorry, it won't be smaller relative to the probability distribution. It will actually get amplified because, like, you know, 0.8. What is 0.8? I'll just guess 0.888, right? Something around that. I think I remember 0.888, right? It will actually amplify, and it will actually become greater in the distribution, right? It's only if, like with these higher numbers, 0.8, that t is over the mark of 1, like 1.5, then only will it actually get diminished, right? But anyway, so what do you have to understand with this? Greater t, t which is greater than 1, causes something called flattening, right? Flattening. And t smaller than 1 causes something called sharpening, which we will look at right now. So here, look at this. You have logits, for example. Let's say you have 3 logits, which are 1, 2, 0.5. Right? This is your probability distribution. Actually, not really, but because it comes from the linear. These are your logits. So you have these logits, and again, logits can be negative to positive infinity, but yeah, t equals 0.6. Now, if you do this math over here, if you do this formula, which is like applied to every element in the logits array, it's applied to that. So you have, so yeah, you put 1, right? So e to the power of 1 divided by 0.6 and all this stuff, right? You do all of this, and you get these values. And if you build a pie chart over here, you had 2 over here. Okay, I like to draw, so I'll just put it over here. you had two dominating like this, right? And it was like this, right? Approximately, okay. You had two dominating clearly, but with this sharpening effect applied, where t is less, mathematically it makes this number greater and the rest smaller, and it creates that little effect where, and by the way, all of this now adds up to 1. It creates that effect where you got this, you got 0.7868, which is dominating even more in this pie chart. It's taking up more space through this thing. It's called the sharpening of the probability distribution, which is clearly greatly represented over here. So you got your logits over here, which are looking like this, right? Like that kind of thing, right? And then they get sharpened to be like this kind of, do you know what I mean? Like it's more sensitive. Like the larger ones get even larger, the smaller ones get even smaller. So like you see that little dump over there, it became even greater. That little peak over there became even greater, and that's the Everest over there. And the reason why this is done is so that this effect on the probability distribution has that, like when we're choosing it, when we're choosing a token, which we'll look at later how it's chosen, when we're choosing a token, the higher probability ones become even greater, and that creates the generation of even more quality text because the higher probability tokens are being chosen. But it makes the model less creative because it's not selecting like something like over here, because it's only selecting these top ones, right? So it makes it a little bit less creative, which is why temperature must be struck with a balance, because conversely, if you make t greater than 1, as we've discussed before, then mathematically it will create this flattening effect. As I've told you before, like if you got Euler's number to the power of 1,000 divided by 1.5, this will become smaller than 1,000, and then it will subsequently make Euler's number smaller than if it was just 1,000, causing a diminishment in the sequence, or not in the sequence, in the probability distribution. And so this is what happens. You had 2 dominating more clearly, but now it's dominating less clearly. It's more equalized. It's more in an equal society where the gender stereotypes don't apply. Okay? So you got this kind of more equalized look, and this is how it would look like. You have this, right? It was like this, and now it's flatlined kind of thing, just like this. This gives the model more creativity because it has more tokens to choose from. It's not just choosing from those two top, it's now choosing from, like if it only had like a specific range to choose from, like this much to choose from, this many tokens to choose from, then it would only be choosing these high probability ones, and that's it. Or like if it only had a range of like how high of a value it could choose from, it would only be choosing from these, right? For example, if it's like, okay, I'm not choosing any other tokens other than these ones up here, then it would be choosing from these only. Whereas if you have that same range, it's going to be choosing more over here, right? There's more tokens to choose from over here. That flattening gives other tokens the opportunity to jump in, but it can result in less quality text. Got it? Okay. So that's something important to cover. Then afterwards, we have our lottery spin. So we've broken down the lottery analogy before, and then occurs the lottery spin. What this is essentially, you can just imagine you have your pie little thing. The person with the most lottery tickets will have a higher chance of winning. I don't know if they allow more lottery ticket purchases, but essentially, like, you got more lottery tickets, so there's a higher chance of this wheel spinning on you and landing on you. It's like a wheel of names kind of situation, where the larger section gets the chance greater. So it essentially first does this either sharpening effect, where like your probability distribution looks like that and now it looks like this. It still adds up to 1, by the way. It still adds up to 1. It used to add up to 1. It still adds up to 1. Or it does a flattening effect where it flattens it out more like this, right? So hopefully that explains it. The wheel is spun, and the one with the greatest section gets the choice. Now here, all of them are of more equal sections, right? So they have more of an equal chance of being chosen. And in that upper one where it's sharpened, the ones that are greater have a greater chance of being chosen. Now, what are the results of this? I haven't actually written them down here. I can just write them with you right now. What are the results of temperature sampling? Well, if the t value is too low, then the text becomes too predictable and maybe repetitive. Kind of like the same problem that we've seen in greedy decoding. If the t value is too high, then the text becomes less quality. If the t value, however, is balanced, t value is balanced properly, so it's like either 0.9 or 1.1, somewhere in that range, is balanced, 0.8 to 1.2, the text becomes both anywhere between this and this, but not this. The text becomes both creative and quality, and of higher quality. So those are the results right there. Now we move on to top K sampling. Which is a very simple algorithm. There's no more math over here. You can literally see that's it. We're just gonna wrap this quickly up. So essentially what it does is you have your probability distribution. Imagine you got 0.4, 0.5, and then 0.1, like literally just 3 tokens in the entire probability distribution. And this is, by the way, a given that linear and softmax has already been applied. Okay? And by the way, sometimes you can use top K and top P together. You can already imagine how that could be done, but we're just going to say that we have softmax applied over here already, just like we would in beam search, in greedy decoding, and so on. Temperature sampling is the only one that replaces softmax. But anyway, you got your probability distribution over here, this hypothetical distribution. Let me just make it more clear for you to see. 0.5, 0.1, there we go. Linear softmax. In this, these are no longer logits, these are actually the probabilities, and they add up to 1 over here. And I've made it specifically so that it could be easier for you to understand. So first, what does it do? You define first a K. Essentially a K is the top K number of probabilities. Usually K ranges between 5 and 50. So like it is, I mean, usually, not always. It can be like 3, it can be 100, whatever you want, but like so essentially you could imagine 5 K 50, approximately about that time. So I should probably make this a little bit longer. 0.2, 0.3, 0.01, 0.09, and 0.2, and then 0.1, and then 0.05, and then 0.05. Okay, these are all the probabilities that I think are now adding up to 1, if I am not wrong. 0.2 plus 0.3 is 0.5. This is 0.6, 0.8, 0.9, and then 1. Yeah, so all of this adds up to 1. This is your probability distribution. Let's say we have a K that's of value 5, exactly 5. And it selects the top highest value. So first what we do is sort the probability distribution in descending order from highest to lowest. So we have 0.3 as highest, and then 0.2, 0.2, and again, and then 0. Just so on, right? And then top K just looks at the first 5, right? Because now the first 5 are the most highest probabilities, and it takes those and selects those ones. And by the way, when we do this sorting, we also have to sort the position. So like this is the first position, this is the second position. We have to sort them around also, so that we have a different array in which we keep in mind which position is which probability, right? So we don't just get them mumbled up and now 0.2 was the first token and now 0.3 is the first token. That should not happen. But anyway, just keep that in mind. It selects the top 5 highest probabilities to do, and then it normalizes them. So essentially what it does is, you can look at this example here. We can follow this example. We got softmax output, sorted from highest to lowest, then top k selects k number of probabilities, these ones for example, then normalization occurs. So essentially for each element in there that is selected, let's say it's selected 0.3, 0.2, 0.2, what else? Could have selected 0.1, 0.1, and then another 0.08, right? Those are the 5 tokens that it's chosen. What it has to do is essentially make sure that this adds up to 1 again, so that it could form that kind of pie chart shape where 0.09 is 9% and all this stuff, and it has like the 9% chance of being chosen and all this stuff. So what do we do to ensure that it adds up to 1 actually? Because this all doesn't add up to 1. What we do is take the sum of this. So like for each element, in order to normalize it, which is the term for making it all making the sum of all of this add up to 1, we do the following. Element divide by sum of elements. So you got the element 0.3 divide by the sum, which is 0.89, and you do that, you get the result, and then you do that for each one, and now you have a new normalized thing, the values of which actually add up to 1. And now you have this kind of pie chart shape, and now you can do the lottery spin as we've done in the temperature scaling, and we select a token at random from the chosen top k tokens. The token is chosen at random, just like the spin wheel displayed above. Larger probabilities are like larger sections, possessing a greater chance of being selected as the next token. Now hopefully you got that. Let me just denote this as normalize. And finally, we move on to nucleus sampling. Nucleus sampling, otherwise known as top P sampling, is also a very simple algorithm in comparison to something like temperature sampling. It essentially is like, it's otherwise referred to as top P sampling because it uses this thing called the P threshold, which you define, which is between 0 and 1. Okay, it's between 0 and 1, and let me just do this quickly. Right, so essentially first we have our probability distribution. Let's imagine we have the distribution that is like 0.4, 0.6, 0.5, 0.1, like this, and it's sorted from highest to lowest, so 0.5, 0.4, 0.1, and the indices are sorted as well, the positions. An indice is just the position that it is like. So this is an indice, this is an indice, this is an indice. We sort those indices as well, so that we have this and this and this, so that we still have a conception of which tokens are which, okay? Because indices are the tokens. So we sort it out 2, 1, 3, right? We sort it out nice and neat, and then we define a P threshold. So P is essentially a threshold, a parameter. So P is essentially a threshold, like a parameter that's like almost like a temperature, where higher values actually lead to greater creativity, whereas lower values lead to more quality. And you have to strike the balance between them. So like the recommended thing is between 0.4 and 0.6, but we're getting ahead of ourselves. Let's just look at this. So beginning from this probability distribution, let's just define one over here. Let's say it's 0.6. Okay, P threshold is going to be 0.6. Now we're going to do this. We have a nucleus that we want to form, an empty nucleus in which there's nothing in it. So we start what's called a collection process, in which we start collecting the tokens or the probabilities of the tokens. and looking at their sum. So we collect this, and with each, this is important to understand, with each step of collection, Top P's algorithm checks whether or not the sum of the collected tokens adds up to or exceeds the threshold P. So let's say we look at this, this does not exceed that, that's like, this is still smaller than that, so we can just add that in, 0.5. Okay, great. Our nucleus now has the value 0.5. Okay, moving on, 0.4, right? We collect that. Oh, okay. At this point now, when they're summed up together, they form 0.9, which is greater than that. So thus, we're done. Our nucleus will thus be the following: 0.5, 0.4, and we should not look past that at that point. It gets to a certain point and cuts off at that point. Now, factually, your probability distribution won't actually look like that. Like a typical GPT implementation has like a billion different, hold on, let me do that, billion different tokens to actually go with. So it's actually way more smaller, like 0.009 and then 0.01 and then all these like small values. So when it actually ends up exceeding, it's probably not 0.9, it's probably like 0.601 like it's approximately there, right? And so yeah, this is the example that I just gave you with 0.6. It collects probabilities up until day when summed up reach or exceed the threshold, making it so that you collected 60% of the total numerical value in the entire probability distribution. Yeah, a realistic probability distribution will like, if you exceed, will be like a very tiny bit above P, but not entirely above P. So if you define if we can conclude from this mathematically, if you define 0.6, then 60% of all the values in there are going to be collected. Not number of values, but like in terms of sum. So like this sum would be 1, and you're getting 60% of that, right? By defining this, you're getting 60% of that by collecting all these values. In reality, this wouldn't be 0.5, 0.4, but it would be like, it wouldn't get up to 0.9, it would just be something small like this. It's essential to understand that it's not actually numbers. The nucleus that you formed may add up to 0.6, or maybe like slightly exceeded by going 0.6001, like, right? It can slightly exceed it, but you've just collected 10k different values and probabilities, but there may be 70k left, which all add up to 0.40 or like 0.30, or what is it, 399, I don't know, man, 88, something like that, right? 0.399988, and they're just like very low probabilities, and these are the highest ones that you've collected. And from that nucleus, you renormalize it again, right? And I'm not sure why I didn't write this. Did I write that? Yeah, okay, so renormalize it, normalize it again, normalize again by going element divided by sum of elements, oh my god, sum of elements, and then there you have it. Choose token at random. We do the normalization again, norm, then random token, random toke, from that like spinny wheel thing. So element divided by sum of elements, we do that so that these could add up to 1 again, and yeah. Now what are the results? Text can be very diverse but of little quality if P is way too high, but the text can be of very high quality but very predictable if P is too low. So again, it's like the temperature thing where you have to strike a balance and get it right, except it's been found that the nucleus sampling method works better for token generation than any other method found right now. So what would our verdict be? Which token method is actually the best for GPTs? That would be nucleus sampling. You could go look into that, and there's a research paper called, what is it, The Curious Case of Neural Text Degeneration, where it actually breaks down how this is done. So essentially they just showed that like greedy decoding, beam search, and temperature sampling, and top case sampling, all of them had some kind of flaws, whether it was just repetitiveness or just degenerate text, all that stuff. And nucleus sampling barely had any of those flaws when the P was optimized, like at 0.6 or something like that, when the P was like properly optimized. So with all this, a single token is generated. You use this method to generate a singular token, and then this singular token is put into the sequence, right? Let's say this token is 5,493, and then it's put into the sequence, and then like over here, that's the last token that you've seen, shoved back into the decoder-only transformer, process it again, generate new probabilities, generate another token, and it keeps doing this until like an end of sequence token is generated or something like that. Now, always keep in mind that each time a probability is selected in any of these token selection methods, its associated position in the original probability distribution is actually used as the token. So I've iterated over this multiple times in this episode. The probability is the lottery tickets bought. The position of the probability is the person who bought it, which is actually like the position. Well, it's actually the token is going to be displayed. So yeah, I hope you found this guide helpful. And if you are just like me and you love AI and you're a young guy who wants to build his own GPT and innovate in this space, please go click on the link in the description right now and go buy the Innovator's Guide. You'll love it.